Hello, everyone, and welcome to our Industrial Data Insights webinar, Predictive Analytics for Improving Asset Reliability and Uptime. We're thrilled to have you join us today. I'd like to introduce myself and my colleague who will be co-hosting with me today. My name is Molly Colwell, and I'm an applications engineer with a background in chemical engineering. I have experience in Six Sigma, quality, and continuous improvement, and for nearly a decade, I've been utilizing data park tools for driving process improvements for operational excellence. Scott, would you like to introduce yourself?
Yeah, thanks, Molly. I'm Scott Carey. I'm a sales engineer here at Data Park, also a chemical engineer by training. Been working with Data Park as a tool for roughly 20 years, but the majority of that time I was actually an industrial customer doing process engineering and optimization and controls engineering work. Joined Data Park officially in this position about a year ago.
Let's take a look at today's agenda. We have a full session planned covering various aspects of predictive analytics for improving asset reliability and uptime. First of all, we'll start out with an overview of analytics for asset reliability, where we'll discuss the types of analytics available today. Next, we'll focus on predictive analytics specifically, exploring the requirements, predictive approaches, their benefits, some concerns and applications they may have. Then I'll pass it over to Scott, and he'll walk us through a few use cases. Two of them are going to utilize data park features, and another is going to utilize a third-party AI. Then we'll have some time for question and answers. So type your questions into the chat. We have a lot to cover, so let's get started. Okay, analytics for asset reliability. Let's talk about how different types of analytics can be leveraged to enhance asset reliability and uptime, as well as some of their outcomes.
Improving asset reliability and uptime can come across as a focused topic, and people may not think about all the secondary outcomes that can occur. Of course, reducing failures and downtime goes without saying, but in turn, this can help decrease maintenance costs because repairs might not be as bad or end up not having a domino effect on other parts if you get them fixed early enough and before they cause major downtime. And with that, you can also help extend the lifetime of the entire asset or individual parts. Quality is another area that can be improved or maintained when we talk about increasing uptime. When you are running more consistently and not going up and down, it's easier to stay within spec and make good quality product. This consistency is going to be the same reason why energy efficiency and optimization is also going to be improved. And also take into consideration the potential for increased safety. By increasing your uptime, thus decreasing your downtime, you're eliminating the amount of time your employees are put in situations where they're out on the floor trying to get the machine back up and running. Depending on your industry, this can be a high stress environment and unpredictable environment. So the less time these employees are out in the situation, the more safe it's going to be. So just because you're focusing on equipment uptime doesn't mean you're working on a single goal. You can actually move multiple needles at once.
When it comes to improving asset reliability, there are several ways we can utilize data and apply analytics to achieve these goals. A good place to start is by understanding the different types of analytics we can utilize. We have descriptive analytics. This focuses on answering the question, what happened? So this would be analyzing historical data. Trends are the key to descriptive analytics. By pulling a few tags in a trend, many times this allows you to show what happened. Maybe you lost steam or there was a spike in pressure prior to an equipment shutdown. This is the key or first step into getting to the root cause. Then we have diagnostic analytics, really understanding why it happened. This helps us uncover the root cause of the issue, allowing us to address them more effectively. Sometimes this is called exploratory analytics and also uses historical data to find the root cause of equipment failures with the aid of downtime tracking software. So sites can assign reason and comments to collect the necessary data needed to analyze events afterwards in Pareto charts, and then go after those events that are causing the reliability issues. Prescriptive analytics is there to answer the question, what should happen? So this builds on the result of descriptive, diagnostic, and even predictive analytics, and provides actionable recommendations and steps to optimize operations. Recommendations can vary from making sure you have proper personnel and parts available to do the maintenance, to utilizing and extending unplanned downtime to do predictive maintenance jobs. Lastly, we have predictive analytics. This aims to answer the question, what will happen? By using statistical models and machine learning algorithms, we can forecast potential failures and events to address them before they occur. This is going to help save money, especially if you can implement just-in-time maintenance, which prevents replacing parts too early or too late, with early warning systems for equipment failures, which in turn will reduce emergency maintenance costs. So predictive analytics will really allow us to drive those predictive and preventative maintenance schedules. Now let's take a closer look at predictive analytics and their multiple approaches. When it comes to predictive analytics itself, there are two primary approaches we can take: artificial intelligence and operational intelligence. We have all heard the hype about artificial intelligence. So AI leverages algorithms and machine learning models to analyze large amounts of data. Then AI can identify patterns and make predictions based on that data and these patterns to predict when issues are going to arise. And on the other hand, operational intelligence is going to use data as well, and even you may have equations at times. But this approach is going to focus on integrating and analyzing data in real time, and it helps optimize maintenance schedules to improve overall asset reliability. There are reasons to use each type, so let's look at each in a bit more detail. Some key features of AI include its use of data-driven decisions. It's using machine learning models to analyze historical and real-time data to make these predictions about equipment health based on its models that it's making. And the fact that it's using continuous learning by getting new data all the time. So the system's going to adapt based on the data that it's getting, as well as anomaly detection. So it's automatically going to identify unusual patterns that could indicate potential equipment failures. So in some cases, these AI models done some learning, it could detect based on a new pattern it sees, hey, this isn't right, it will shoot out a higher anomaly value because it doesn't recognize this pattern. Some applications of AI in manufacturing, of course, is going to be that predictive maintenance to forecast equipment malfunctions and help us schedule maintenance to prevent downtime. Then there's quality assurance, so we can predict and prevent defects by analyzing variations in production. Or even we could use it for supply chain optimizations to predict maybe supply and demand issues to optimize inventory or logistics. Some benefits of utilizing AI could be reduced downtime. If we're able to be proactive about maintenance and we're able to couple these predictions with prescriptive analytics and actually take actions, then yes, we can reduce unplanned downtime, which in turn will increase our efficiency. Optimizing machine performance and maintenance schedules lead to higher operational efficiency and thus saving money. As we talked about earlier, preventative maintenance costs can help reduce our emergency maintenance costs and maybe help prevent that domino effect. However, there may be some considerations to take before jumping on the AI train. One is your site's data quality and quantity. In order for this to be a success, it really depends on your data.
AI is going to take a large amounts of data and high quality data. Without the data, you're not going to go very far. So make sure that you have high quality, comprehensive data sets for both good periods and bad periods, so you have a learning model to start with. Skilled resources. Many times, in order to get this started, you're going to need skilled personnel, subject matter experts to help develop these models or even maintain them in some cases. So these can be complex to get started and even to get trained. So depending on which tool you're using, you're going to need a subject matter expert or a skilled resource to be able to help interpret and feed that information to the model. And finally, integration capabilities. The system must be able to integrate with existing IT and operational infrastructure. If you have the data and you have good quality data, it's not going to be very useful if you're not going to be able to integrate with that platform that can read all this data. So make sure before selecting an AI or machine learning tool that you have the integration capabilities that you want for both IT and operational infrastructures. Some typical features of operational intelligence is real-time data processing, analyzing the data it generates to provide instant insights, contextual insights, so integrating data from various sources to provide comprehensive view of operational performance, and event-driven alerts like limits or alarms to trigger alerts based on predefined thresholds. Some examples for applications for operational intelligence within manufacturing could be operational efficiency, so monitoring performance metrics against a benchmark or a limit to help identify deviations, to identify potential equipment issues. So if that value is starting to trend outside of a line or a limit, you could get an alert or identify something is going wrong. Process optimization, using that real-time data or those real-time trends to fine-tune production processes or maybe center lines to help reduce waste and improve yield, or even maybe safety and compliance monitoring. This could ensure that operations are staying within those regulatory parameters, maybe your environmental parameters and safety standards to help reduce risk. Some benefits of operational intelligence. It's very likely that this technology is already at your site, whether you're using Data Park tools or something else. But since you already have it, it makes it that much easier that you're going to be able to continue to integrate it into your site and get more data should you need it. It's very cost effective. It's typically less expensive than AI, even when implementing a new system or other IT projects, since, again, it's building on existing infrastructure. And you're leveraging in-house knowledge, because not only are you leveraging engineers' knowledge, but you're also leveraging operators, supervisors, superintendents, and everyone on the operation floor. Some considerations to take is that if you are using a new system, you want to make sure that it does integrate with your existing operational system or your IT systems. You don't want to bring a third-party operational system in that doesn't work well with existing systems. And lastly, before I hand it over to Scott, I want to take a moment to speak about data. To effectively implement predictive maintenance, quality data is a requirement. Accurate and reliable data is critical to identify patterns and signatures for failures. This data typically comes from sensors or maintenance records. Data historians also play an important role in storing and retrieving vast amounts of data that is necessary for this analysis. SCADA systems are also really important for collecting real-time data from all of the devices across the plant. And ideally, all this data is integrated into a single system, which unifies the approach and simplifies the analysis. Whether you're doing operational or AI, it's important to have it in one place and have a single source of truth. If you're going to go the route of third party for artificial intelligence or operational intelligence, you need to check that integration is going to be compatible with your data. This is going to be the foundation to ensure that you are going to be able to do the analysis and get it back into your data visualization tools so you could be alerted effectively. An analytics-based approach in maintenance relies on compelling data from multiple sources to uncover patterns and signatures of failure. A comprehensive data set is the foundation for effective predictive maintenance, allowing us to anticipate and address potential issues before they lead to equipment failure. So with that, I'll hand it over to Scott, and he'll take us through some examples.
Thanks a lot, Molly. With those concepts in mind, we're going to go through several examples here of how we can use data and predictive analytics to help drive maintenance or quality and overall asset reliability. In the first case here, we're going to look at a grinding wheel process where the grinding wheel is a wear part. So here we see grinding wheels, normally they're in production and operation, and they can be resurfaced. So that's a maintenance activity that can keep them going, but eventually they wear out and they have to be replaced. So we want to make sure and optimize this cycle of production, maintenance, and replacement on these grinding wheels. So the problem was that the resurfacing the wheels was happening too often. Operators, without any data or information to really understand how often it needed to happen, they were just resurfacing between every batch, which was really, in a lot of cases, more often than necessary. They were also at times trying to continue resurfacing wheels that were actually worn out and should have been replaced, but they didn't have a good way to really know if that was the case. So looking at solutions, this is where we have to start making sure that we tailor the analytics solution to the problem at hand. Really, from a first principle standpoint, we know that the grinding wheel's wear rate is based on really only two factors, and that's the length of time that it's been in service, in operation over here, production, and the material that it's been grinding on. So there's different hardnesses of material that it could be processing. And so as long as we have a piece of data telling us which material it is, then we will know for how long it's been in production, how much it's worn. So we can build a calculation for that. And it doesn't require any big data models. It doesn't require AI. It basically just requires setting up a simple formula in a calculated tag in your data analytics system. And DataPark has several ways to achieve that. Once you've got that calculation in place, then you can build a daily report that will show the results of that calculation to basically indicate the life of each grinding wheel and how much is left, so that you can keep an eye on the situation and be ready when it is time to either resurface or replace them. In addition to that, with this wheel life calculation, we can set up alarms and notifications if any of them are getting to a point where they're in danger of being worn out enough to cause downtime or quality issues. So those are all things that we can apply. So here's a little bit of a more detail on that wheel life calculation. So essentially, you can see in the trend examples here, when the wheel is in operation, you'll see the wheel life dropping, and the slope of that descent might be a little different depending on what material it's processing. So, and then the flat sections of the trend here are periods when that grinding wheel is not in operation. So obviously it's not losing any life when it's not being used or worn out. So that calculation creates this trend, and it's not really that complicated, but it's something that would be difficult to just estimate in your brain at any point, especially if you don't know what happened yesterday or the day before, if you just came on shift. The other thing that's useful here is the projected data. So in DataPark, there's the ability to turn on projections for trends. And what that does is uses some simple algorithms to project the kind of average recent slope of the variable out into the future. So this blue vertical line here would indicate current time on this trend. And then we have a projection into the future of how much longer that particular grinding wheel is going to last in this case. That's what the projection would represent. So if we see that this projection is going to reach zero before in a shorter time than the next batch will take, then we know that we need to take action. We need to either do a resurfacing or a replacement on that wheel. Here's an example of a simple report that could be produced based on that age and condition report or calculation on the wheel. So you can see here, if you've got multiple grinders, you could create basically a status, and that could be triggered off of how much life it has left. Maybe if it has any more than 3 days of life left, it's still good. If it's less than a certain amount, then you could have a schedule replacement. And then ones that are near or at 0 life left, you could code those red and say needs replacement. And so it's a simple summary that could be produced every day or every week, or depending on the overall life of the grinding wheels, and sent out to those folks who are in charge of maintenance there on those. The other thing, like I said earlier, is you could create an alarm. So when the calculation says that there's a less than 20% of the life left, have that alarm visible on the operator screen so they're alerted and they don't continue operating to the point where their grinding wheel is completely worn out and then causing quality problems or perhaps downtime. You can also email a notification based on that criteria, maybe a little lower criteria, or however you want to set that up. So in summary, you could use data to notify the right people when the grinding wheels need to be resurfaced or replaced. You can calculate a simple projection to look and see whether there's enough life left to complete the batch that you're planning. And then you can create reports and alarms based on that calculated life of the wheels. And the pros to this are you're going to reduce cost with you're not going to be changing out the grinding wheels as often. You're not going to be spending labor hours resurfacing them when it's not needed. And you're also going to have more reliable operation because you won't have the downtime failures or the quality failures due to grinding wheels that are not being maintained properly. It does require a little bit more data, although in this case, this is a very simple calculation, only requires a couple pieces of data and a little bit of time to set up the calculations. And of course, someone has to be involved that understands the process, right? Someone that can know for each material that you're grinding, what's the wear rate for every hour that the wheel is in operation. So someone's got to enter that information into the calculations. But this is a good example of a simple application where we don't need a 747 to get from here to the next block. We just need a small car, and this is a small car, and it's taking care of us just fine. So another case study here is where we have a quality value that is only measured in the lab. So let's take a look at this one. So in a lot of cases, we measure quality of various products or intermediates in the lab, and that of course takes time and labor. So we don't always get those lab samples and their results very quickly. And it would be very helpful to maintain operational reliability and quality if we had a real-time indication of that quality parameter rather than waiting 2 hours or 4 hours or however long it might take in between samples and analyses in the lab. So the solution is to build what we call a partial least squares, abbreviated PLS, multi-input model of that quality parameter using real-time input data. So this is a multi-input single output model. Partial least squares is a linear modeling technique, and it's available in DataPark's Park Model tool. And then once we have that model built, we can apply model corrections with lab data feedback using a calculation in, again, in DataPark's calculated tag function. So we're going to use Park Model, which is, again, that PLS modeling tool. We can use limits to set up alarms based on the model results. And of course, we're going to use trend to view the model results, and the lab data is contained in our manual data entry system, which is abbreviated M. So this example is a steam heated pulp dryer in the sugar beet processing industry. So moist pulp comes into the dryer, gets processed inside and dried to a certain moisture content, and then that exiting pulp is its moisture content is measured by lab sample only. So it's a fairly long gap in between lab samples based on the when they're collected and how long it takes to analyze it, something like 2 to 4 hours. So the problem was that that was just not frequent enough to properly control the process. And so in between lab samples, operators would get concerned about the moisture content and frequently over dry the pulp. So you'd end up with a lower moisture content on the outlet than was necessary. And when you've over dried, that means you've evaporated more water in the dryer than you needed to, and its capacity is based on evaporation. So over drying causes lost operating capacity. So the solution was to build a multi-input PLS model to predict the moisture of the dried pulp as it exited the dryer. And that information would be available real time in between sample results. And then we set up limits and alarms based on that calculated value, that predicted value, to monitor the process and make sure that we were within spec. And also, and this is key, we can model, we can look at the correction factor between the modeled result and the actual lab data that come in every few hours, and make sure that that correction factor is also not increasing too high using alarm limits. So again, the solution is to build a multi-input PLS model. We're going to use primarily continuously measured input variables that we know have an influence on the output. So here's where that process knowledge comes in again. Someone that's familiar enough with the process to know which input variables affect that pulp moisture would put together this list to build this model. In this case, we're looking at the incoming pressed pulp moisture, so that's the wet pulp that's entering, the metering screw speed, which is essentially the feed rate to the dryer calandria pressure, which is how much heat we're adding to the system, and the dryer dome pressure, which is basically the pressure on the pulp itself before it's discharged. So we put all these variables into a trend, and then choose a training data period, and then send that data from the trend directly into Park Model, which is basically just a right-click, easy transition in DataPark. And here you can see an example training data period where we have the black trend is the observed data. These are lab samples, each dot, and the blue trend is the predicted data. And it's not perfect, but you can see that the prediction does follow the trend pretty consistently. And then if we look at the model fit on a XY plot, we see that it has an R squared of 0.634, which again, not perfect, but good enough to get an idea of what's happening in between lab samples. Then what we do is use that modeled value and compare it to the lab results each time they come in, and build an offset correction factor so that we account for any model drift, and we also monitor the quality of the model so that if we see that offset running too far off one direction or the other, then we know we either have a measurement issue with one of the inputs to the model, we have a measurement issue with the moisture itself in the lab, or we have some sort of process change occurring in the dryer. So that in itself is a piece of predictive or at least monitoring for maintenance purposes, is whether the model still matches the process as it did during the training period. And then of course we have the modeled pulp moisture value itself. So in this trend, you can see early in the time period, we had a couple of episodes where the pulp moisture went below the low limit here, the red line, for significant periods of time. But what happens is after a while, the operators start to gain confidence in the modeled value, this green line, which is in between, showing us what's happening to the pulp moisture in between lab samples. And pretty soon they'll start controlling based on that modeled value instead of waiting for those lab samples to come back. And by the end of this time period in this trend, you can see how variability was reduced and the average moisture was approaching much closer to those high limits, which is the more efficient way to run. We're going to get higher throughput because we're not evaporating as much water unnecessarily, and it's a more consistent quality product. So now let's talk about one more example. This one is kind of taking another step into a little higher complexity and utilizing artificial intelligence. So in this case, the problem was, and this is kind of in retrospect, the problem was identified as a retention aid supply tank. It's a chemical mix tank that had an agitator that had come loose and fallen off and caused problems in the process. And this chemical is critical to the process, and if it's not supplied in a uniform consistency and rate, then there's either quality problems or potentially even downtime, because this is associated with a paper machine, and if the sheet breaks, then there's downtime. The solution here was to use an AI model with anomaly detection to determine if there were any signs of failure and associated with the pump that was discharging out of this tank. So the tools that were used was, of course, a lot of data. That's part of AI. One of its key things to know is that it requires a lot of data. And so that's where ParkView comes in, is to provide all that data in one single source of truth, one interface to a third-party AI tool. So that's, in this case, we're utilizing something where the data goes up to a cloud calculation engine, and the actual AI model is calculated outside Data Park, and then the result comes back to Data Park, and we can build some alarms based on that. So the sort of flow of data and information in this instance would be, we start with a large pool of data in Data Park that about the paper machine process. So there's all sorts of parameters included here, and we send that data to the AI tool. And again, this is a calculation engine in the cloud. And we do have to define some training periods that we would classify as normal operation. Again, still in every case, no matter how complex or simple it is, we do need a subject matter expert to at least define some boundaries and some parameters for these models. In this case, we just need to define the normal periods of operation, and this cloud AI model will train itself on those periods. And then as we continue to utilize the model, we can keep identifying more normal periods, and the model will continue to refine itself and kind of sort of self-learn based on that. But again, we have to tell it what is normal operation. Once it has a good base model of normal operation for this process, the model can then start calculating an anomaly score. The anomaly score is essentially a probability that the current operation is outside normal limits as a whole. That anomaly score then gets sent back to Data Park, where we've created a tag to historize it. And then we can set limits on that anomaly score to create alarms and notifications based on that. So in this case, in this example, the paper machine anomaly score, you can see this green trend here. It was basically 0 for quite a while, and then it started to show some activity and then started to rise. And this occurred quite a few days, something like 5 days prior to the actual failure, which is this downtime event over here about April 10th. So you can see the anomaly score climbed as the issue was manifesting itself, and then it reached a kind of a peak and stayed plateaued there for a while, right up until the downtime occurred. So if we had had an alarm on this anomaly score, say at 70%, we would have seen that alarm several days before the failure occurred. Now, by looking at this trend, all you can see is that there is some anomaly. Something has changed in the process. It's not running within normal boundaries. What you don't know in this trend is what's caused that. But these AI models are capable in a lot of cases of producing a list of contributors to the anomaly. So as the anomaly score is rising, you would also have a set of probabilities that individual input variables are contributing to this anomaly. And we don't have a trend of that here, but that information could then drive your investigation into what's causing this anomaly, and perhaps you would see some, some high scores on the pump coming out of the tank, or maybe the agitator amps on that tank, and you'd go and you'd find that agitator broken, and the fact that retention aid chemical was not being mixed properly. So the pros of this type of analysis are that it allows you to detect failures before they occur. And then, if you can see this several days ahead of time, you can plan a short outage to take care of the maintenance that needs to be done. And that's going to be, you can do it on day shift instead of on a weekend night shift, and you're not paying overtime, and it reduces the cost to do that. Of course, the cons of a full-blown AI model is it requires a lot of data. So you're going to need to input or interface with that system a lot of data. And as with all the rest of these methods, it's going to require someone with subject matter expertise to set up the model. In the case of AI, it isn't necessarily requiring a lot of first principles expertise, because the model is using empirical mathematics to build itself. But it does require understanding, what's normal, what's not, what's uptime, what's downtime, and being able to select those periods and input that into the training data set. So to summarize, there's a lot of different use cases for data in analytics that contribute to asset reliability. And so you really just want to, before you start applying a solution, think about, does the solution fit the use case? Because the use case needs to drive that. It needs to, if all you need to do is a simple calculation, then that will be a much less expensive and easier to maintain solution than a full AI model. But in some cases, you do need a lot of data and a full AI model to fully describe a process and detect all those sorts of anomalies. But the thing to just make sure that you're not doing is taking a solution and trying to fit it to a problem. Make sure that the problem drives the solution. And with that, I think I'll wrap up my portion of today's webinar and turn it back over to Molly to close us out.
Yeah, thanks, Scott. So our first question is, with the recent press regarding deceptive AI models, are there any concerns about the industrial AI intentionally returning incorrect results?
Yeah, that's actually a really interesting question. Thanks for asking that. And I've read a few of those articles lately. But one thing I think that's key to kind of differentiate is, most of the AI that's being discussed by the popular media these days, and everybody is sort of getting excited about it outside of an industry, is large language models. And that type of AI is based on probability of words and how they typically are associated with other words. Whereas the industrial AI that we were referring to today, I think is more, I mean, I know it's more mathematical based, right? So it's utilizing, numbers and mathematical formulas to evaluate data and produce predictions. So I think there's less chance of sort of intentional deception there, because there's, math, 2 + 2 always equals 4. It's not up for interpretation like language can be, depending on the individual and what the training data set is for language. So yeah, interesting question, but I do think in industrial analytics, there's a much lower probability, much lower chance of dealing with sort of intentionally deceptive models.
Cool. And then we have a question about, is this presentation going to be offered again, or if the recording is going to be offered? So yeah, this presentation recording will be sent to you in 3 days with a link to the recording on YouTube. So that's where it will be, and yeah, it will be emailed to you directly, or for anyone who registered, if they missed it, they will also get the link to the recorded webinar as well, and it will include this Q&A session. Another question we had, what would you say a good period of time would be, or how much data would you need to define a good period? Would that be days or months or years for predictive, for an AI model to like learn a good period, or even one of our PLS models to learn a good period?
Yeah, that's actually an interesting question, and it's one that you really have to evaluate on a case-by-case basis, because it's driven by several factors. First of all, what's the time constant of the process? Is this a process that has changes and responds to inputs within seconds? Or is it a process that has long delay times and long residence times, and you might not see a change to an input until a day later? Because very fast processes can be trained with much shorter time spans than long, slow responding processes can. The other thing to look at is what's the frequency of anomalies, or even just measurable process changes. Some processes run in a very steady state for a long time and only see major changes periodically. So you got to look at it, make sure you're getting enough of those major changes into your training set in order for the statistical significance of them to add up well enough for the model to be trained well. If you've got something with a lot of variability and it's covering the entire operating range of its process capabilities in a short period of time, if that all happens in 1 day, you may only need 1 day of training data for your model. That's not typical, though. Typically, you need to collect more like several months of data in order to catch all the potential combinations of input changes and output responses.
Yeah, great. And then we have another question about the calc tag for the grinding wheel resurfacing. And how would that calculation know that it was resurfaced? There are probably a few different ways that we could do this, but yeah, how would it require user input or a different tag to maybe indicate that something was resurfaced?
Yeah, I think there, like you said, there's a couple of different ways. If it's a manual resurfacing process, because I wasn't personally involved with this example, so I'm not sure exactly what the resurfacing process involves, but if it's manual, then you could have a manual data entry point in Data Park where the operator just basically checks a checkbox to say, hey, I resurfaced this wheel on this line, and that would indicate to the calculation that it needs to reset. Or if it's some sort of automated resurfacing process, if there, a robotic arm comes down and resurfaces the wheel, in between batches or product runs, then that could be automated. You could have a data point come out of that robotic system to let the calculation know it needs to reset. So it just depends on exactly how the resurfacing process works, but in any case, you do need some sort of indication from, as a flag in the system to let it know.
Yeah, but yeah, definitely a tag with some sort of timestamp that it can go off of, and that would be your indicator. Yep. And then maybe looks like maybe we have one more question. So someone was looking to do projected data and they had a calculation, but they were having trouble making it project in ParkView. So do you have any pointers for that?
Yeah, there's a couple of things, a couple of steps you need to take to enable that projected data in Data Park. The first one is on the data source, where that tag is coming from in your source configuration. You'll need to select the projection template, and you'll need to have administrative access to source configuration to do that. But that basically tells Data Park, how do I calculate or where do I look for the information to know what this projection should look like. And then in the trend itself, in trend configuration, you'll need to set up a projected time span. I think the default is something like 2 hours, but you want to make sure that there is a positive projection time span set in the trend configuration as well.
Yeah, that one can be a little tricky. Maybe that's a good quick tip, my next one to do.
Yeah.
Okay, I'm not seeing any other questions come in. So we'll go ahead and wrap it up here. If you do have any other questions, there's a survey at the end. You can definitely submit them there. Or if we miss them as we're closing up, we will get you in an email later. So thank you for joining us, and we will see you next time. Have a good one. Bye.